Hello. Let's try to solve this question together. We are calculating the probability of the sample average smaller than zero. And to calculate that probability, we are going to use the normal distribution. And so first, we are going to calculate the mean and the standard deviation of the sampling distribution. And we use the mean and the standard deviation to standardize that probability, and then you will use a calculator or Excel or table to find the answer. So these three steps. So in the first step, calculate the mean and the standard deviation for the sampling distribution. And we already calculated the mean and the standard deviation of a single outcome, and that was 200 and 900, right? So remember, we calculated the expectation of a single x and standard variance of a single x, single person, and use the same number, but the difference here is the mean does not change. The mean does not change, but the standard deviation changes because now the sample size is 10,000. So square root of 10,000 equals 100. So the resulting standard deviation for the sampling distribution is 9, which imply the probability, the parameters for the normal distribution, sampling distribution, is 209 squared. So variance. Then using those two numbers, standardize x bar into a standard normal distribution. So x bar becomes z, and the right hand side 0 minus 200 over 9 equals minus 22.22. If you search for this probability on a calculator or on Excel, you will find 0. Remember, the rule of thumb is that the standard normal distribution has most of its probability between plus minus 4. Maybe 99.999% lives within plus minus 4. So minus 22 is a very, very extreme outcome. So in the end, the probability is 0. So what it says here is, as the sample size increases, the risk disappears. So virtually there is no risk of loss. So this is, so X bar was the average profit per policy, which is 0, right? The insurance company has no risk in the end, as long as the sample size is large enough, right? This is the proof, like illustration of how the insurance market works, or how the risk pooling works, based on the law of large numbers and the central limit theorem. Isn't it interesting? Okay, I will, and as a last example, I'm going to compare the sampling distribution theory, the central limit theorem, with the binomial distribution, because by construction, the experiment for the binomial distribution involves multiple experiments. Do you remember? So in the definition of a binomial distribution, you repeat a binary experiment for n number of times. That was the starting point of the binomial distribution. And we count the total number of successes out of n trials. That's how we define binomial. And we are going to, so we may approximate the distribution to a sampling distribution using the central limit theorem. Here, let me think about this. So in the binomial experiment, you repeat a binary experiment again and again. So a single experiment is a binary experiment, but you do that for n number of times, right? Like Um, so and then based on the binary random variable as a single experiment, if you calculate the sum, it becomes a binomial distribution. We are going to denote it as y. So y is the sum of the outcomes. If you take the average of the n binary outcomes, then it converges to a normal distribution by the center limit theorem. So depending on whether you calculate the sum or the average, you may use two different distribution. So either binomial or normal distribution. So however, they are closely related. So sum and average are not totally different. They are closely related to each other. And in many applications, actually the average may be more useful depending on the applications, but actually they may be converted to each other. So I will show you an example. We are going to consider the overbooking example we considered earlier in chapter 5. So an airline company accepts 400 reservations for a flight, but the flight has only 370 seats. So the airline company overbooked 30 seats just to maximize the revenue. And as before, the probability of cancellation is 10%, and implicitly I assume that all reservations are independent with each other. And we would like to calculate the probability that 30 or fewer reservations are canceled, which means the airline company is in trouble. Like there are not enough seats than the passengers who want to take the flight. So we are going to calculate this. First, remember you may use the binomial distribution. Binomial distribution, say y is the number of cancellations. Number of cancellations with parameters 400 and 0.1. So out of 400 reservations, you have probability of cancellation with 10% each reservation. And then using Excel, you can calculate the probability that y is smaller than 30, smaller than or equal to 30, which is 5.239%. Right? We like it's not you cannot do it by hand, but Excel can do it or a calculator can do it. And this probability is not an approximation. This is the exact probability. Exact probability using the formula we derived in chapter 5. And however, like it's not easy to calculate. And when you have much larger number here, even a computer may take longer time to calculate the probability. But if you are willing to sacrifice some approximation error, the calculation could be much easier. Now we are going to use the center limit theorem by converting the variable y into the average. So y is the number of cancellations, and I am going to divide it by n. So out of 400 reservations, y number of reservations are canceled, which is the average. So this equals the average, right? So because y is the summation, sum divided by the sample size equals the average. Or this is the cancellation rate, so it's average. Then you have to divide y by n. You have to do the same thing on the other side to keep the inequality unchanged. So 30 divided by n is on the right hand side, which equal n is 400 now. So the right hand side becomes 0.075. So the probability that the number of cancellations is smaller than 30 is equivalent to the probability that the proportion of canceled reservations is smaller than 7.5%, right? So 30 out of 400 is 7.5%. So basically, we are working on the same numbers. And then the reason why we are doing this is because the central limit theorem applies to the average, not this guy. So this guy with y, you may use the binomial distribution, but not the central limit theorem. If you want to use the central limit theorem, you have to convert it y into x bar, and the relationship is based on this. So y was summation, but the average is calculated by dividing by n, right? And then the next step to calculate this probability, you have to calculate the mean and the standard deviation of a single outcome first, and then calculate the mean and the standard deviation of the sampling distribution, and then standardize the probability using the mean and standard deviation, and then finally use a calculator, use Excel to find the standard normal probability. There are 4 steps. So step number 1, the mean and the standard deviation of a single outcome. It's simple because, remember, single outcome means the result from one reservation. One reservation is one outcome, and it is either success or failure, cancellation or not. So it follows a binary distribution, which has very simple form. The mean is P, probability of cancellation. Variance is probability of cancellation times probability of non-cancellation, which is 0.09. Taking square root of this gives you the standard deviation, which is also simple, 0.3. So for one reservation, the mean is 0.1. The standard deviation is 0.3 for one reservation. But now you have 400 reservations. The mean does not change. The mean is the same, 0.1. But the standard deviation of 400 reservations is inversely proportional to square root of n. So single outcome standard deviation is divided by square root of 400. Square root 400 is 20. So you get this number. And then you get the mean and the standard deviation of the sampling distribution. Apply the central limit theorem. That means we are going to standardize this guy into this form. So x will become the standard normal distribution, and the right hand side will be standardized in the same way. Subtract mean, divide by standard deviation. And the right hand side is minus 1.666666. So I rounded at this point. So then the result is 4.779%. This is an approximation. So compare this result to this. This is the truth, and this is approximation. You may think there is an approximation error. The difference is the approximation error by like the central limit theorem. So the approximation error may still exist, but it will decrease as the number of reservations increases, and obviously much easier. So the larger the sample size is, binomial distribution becomes more and more complicated to calculate. It will take more time, more computational power to calculate the binomial distribution. But the larger n is, the more accurate the normal distribution is. So as n increases, binomial distribution becomes less attractive, but normal distribution becomes more attractive. So that's a simple trade-off between them, and that's the relationship between these two guys, and remember, normal distribution is just an approximation. Okay, this is the end of this chapter. We are going to go to the next chapter, which is about estimation. That is the most important chapter of this course. Like estimation, as you can feel, it's the most important part of statistical inference. So look forward to that. See you later.